All right, how's it going, everybody? We are here on Tuesday of week 10. Yesterday, we introduced our ideas about confidence intervals. We looked at our first and simplest case of confidence interval. Today, we want to expand a little bit to two other scenarios, both of which are very, very practical to us. So, realistically, what typically is the case here is that for both hypothesis tests and confidence intervals, it's pretty typical for us to first look at this Z statistic associated with hypothesis tests and confidence intervals, like we've done. You can see at the top of the screen here. But it's also the case is that these are typically not what we see crop up in real life, but they are uh, I think our least weird scenario. So in learning these things, it's very, very common for this to be the first thing that you learn. But it's also the case that these are not necessarily the situations that we're going to expect to run across in the real world. And so really the two that we're looking at today are, in a sense, are more practical tests. There's nothing wrong with the one that we did, except for just how unusual the scenario itself actually is. So let's take a look and see what we saw. We want to make sure that we're drawing very close parallels today to the hypothesis tests that we looked at last week. Um, what we saw last week with our hypothesis testing is we saw three different formations of our hypothesis test. And so we're going to quickly go through those right here and then identify that we're going to see the exact same distinctions with our confidence intervals as well. So when we looked at our three hypothesis tests, what we saw were these three cases. First case, the first one that we looked at, our first hypothesis test said, if we want to make statements about a population mean, mu, and if we know the standard deviation, sigma, then we can use our standard normal distribution, our z distribution, to compute our sampling distribution probabilities. In this case, we had an individual from the population that was distributed normally with mu sigma here, but what we maybe more importantly want to say here is that our sampling distribution is distributed normally. Our average is still mu, but we got the sigma over root n. And the important thing for us to see here is that our average is always this term after the subtraction, and our standard error term, sigma over root n in this case, is always our denominator of our fraction right here. So in these cases, in the hypothesis test cases, again, I'm kind of talking about last week instead of yesterday here, or last week instead of previous video here, that our test statistic in our hypothesis tests was computed like this here. This is our measure of number of standard deviations. We found how far our sample average was from the population average, and we divided that by the number of the size of a standard deviation to get the count of standard deviations our sample was away from what would be expected. Then we said, that's actually kind of weird because the whole point of this is to make some claim about mu. Mu is the population average. How is it that we don't know what mu is and we do know what sigma is? Sigma is the population standard deviation. So the unusual thing about this scenario is we're claiming that we don't know one population parameter, but that we do know another. But how would we ever know sigma if we didn't know also mu? Like any data that we'd collect that would give us sigma should have also given us mu along the way. So this is not necessarily a scenario that we expect to find ourselves in often. So then we updated and we said, all right, if we want to make statements about the population mean mu and we don't know the population standard deviation sigma, much more common, in this case, we're still going to take a sample though, right? We're still going to sample n people or n observations and see what we see. So in this case, we should know the sample standard deviation. Most important word there is sample versus population. We do know the standard deviation just from the little sample that we took. We call that guy S. And so instead now we say, all right, we can't quite use the normal distribution because the normal distribution depends on us actually knowing sigma, and we don't. So instead, we're using what's referred to as the student's t distribution, or just t distribution. And in the t distribution, there are lots of different t distributions depending on the size of our sample. And kind of what we want to say here is that using the t distribution is sort of an admission on our part that says, listen, we don't quite know as much information as we would hope to know. We sort of hope to know sigma, but we only know s. So instead of having a normal distribution that is nicely shaped up to represent lots of middle area right here, we have less confidence about where things are. And so we get our distribution to be quite a bit more spread out. So it's still sort of bell shaped, But when I hear people say bell-shaped curve, that means to me a normal distribution shape. The t-distribution is technically not quite shaped in the same way that the normal distribution is. So they do look very, very similar to each other. But they're a little bit different, and it depends on how big the sample size is here. You should see here that we're saying that x is distributed according to the t-distribution with a sample size of n, or sometimes this is listed as t sub DOF. Um, Maybe I'll say or t sub degrees of freedom. And remember that our degrees of freedom is just one smaller than our sample size right there. We get lots of those t-distributions out there. There's a different t-distribution for every individual sample size that there is. Every number of degrees of freedom, there's a slightly different shaped bell curve that's out there. As our sample size gets larger and larger and larger, the t-distribution gets closer and closer and closer to just being the standard normal z distribution there. So in this case, we updated our test statistic, but notice how minimally it changed. The only thing that changed is that we just got an S in place of sigma. They're literally even representing the individual standard deviations. This is just a population instead of a sample right here. All the other terms stayed the exact same. So barely an update right there, but computing the probability that we would see t values like this, we get different answers than the probability that we'd see z values like those. This, we computed these probabilities with a z distribution. Here we compute the probability of seeing events like this with a t distribution, and those aren't quite the same. So the probabilities are different, even though the test statistics are hardly distinguishable from each other. Finally then, talking about some proportion statements here. If we want to make statements about a population proportion P, so this is quite a bit different than the previous two. Both the previous two were us trying to make statements about our sample or our population average mu. But alternatively, we could talk about population proportions, P, for categorical questions, for binomial questions. Male, female, smoke cigarettes or not, support a candidate or not, drive a car or not, college student or not. Lots of these things, we're talking about a proportion of the population, and we might want to make an estimate as to what proportion of the population has some certain feature. In this case, we can use our standard normal distribution to compute our sampling distribution probabilities. And in this case, notice that our test statistics still took on the exact same form as what we saw before. By the way, quick little notational thing. I kind of mixed some notation right here. The book seems to be using this prime notation. I would verbalize this as P prime when you put that little apostrophe on it right there. This is actually the first time I've ever seen somebody use that notation, but it still makes sense to me because it's still similarly matching the what I've seen more typically, which is the P hat notation right there. In either case, the standalone P with no marker on it, just a bland old P right there, that is the true average of the population. That's the true population average. If we're using either the P prime notation or the P hat notation, in both cases, this is the sample proportion. So let me just kind of notate this here. Population proportion is this guy, or our sample proportion. Just what did we get from just the sample that we took? That's either one of these two guys. So I'm down with either one right here. As long as you're distinguishing P with nothing on it means the population's value, and P with something on it means the sample's value, then we will not have any confusion here. So again, really importantly, see that while this kind of looks like a gross and hairy formula right here, it's the exact same structure as our previous two. Our structure here is that we have the sample statistic, P hat, X bar, it's what we got from the sample, minus P, or mu, what we know from the population according to the null hypothesis, divided by whatever term is sitting in here for our standard error term, right? Sigma over root n, that's what we divided by. Square root of PQ over n, that's what we divided by. Whatever's sitting in the secondary slot, our sample standard, or our standard error, that's always what we're dividing by over here. So it's important to see that these all have this exact same structure. The number of standard deviations away from average that we're estimating our sample to be is always computed by our sample statistic, either P hat or X bar, minus our population parameter, either P or mu, divided by our standard error term, either S over root n, sigma over root n, or square root of PQ over n. So it is maybe the case that we need to look some of these up sometime. That's fine. Recognize that these all, while all the three of these formulas look different, they all have the exact same structure. We're getting all the pieces of information from the exact same place. Our word equation down here is the exact same for all three of them. This is exactly the word equation I would use to describe all three of these scenarios here. So it's good to kind of like take off the horse blinders for a second and see that when you stop looking at the fine detail of each of these, their structure is exactly the same, and that's going to keep following us. As I've said to you guys a couple times now, we still have several more hypothesis tests to go, several more confidence intervals to go, and it's very, very useful for you if you recognize right now that the structure of the equations that we're looking at here won't change pretty much this entire time. We're going to keep computing test statistics the same way. So, and by the way, maybe just real quick, look above my head right now. What we're going to be doing next week, you can see the next lecture is 10.1, 10.2. That's comparing two population means. So this is going to be saying things like, is there a statistically significant difference between the average height of men and the average height of women? We're going to collect a sample of men and we're going to collect a sample of women. That's two samples that we're collecting right there. But what we're going to end up seeing is that the structure of the test statistic that we compute, even though there's going to be more terms in it because we're going to have two samples that we've collected, there's going to be two population averages that we're thinking that we're comparing against. So we're going to have more values in here. It's going to be technically different than these, but the structure is going to be the exact same. We're still going to get sample stuff minus population stuff divided by standard error stuff. That's not going to change. So I'm restating these here. I'm talking about hypothesis testing during a confidence interval day right now because we want to make the exact same distinctions for our confidence intervals, exact same distinctions. Our math is going to be changed in the exact same way as we just saw in those three comparative scenarios above. Last video, we saw the first scenario, a confidence interval for mu, a population average, where we did know sigma, the population standard deviation. As I keep on pointing out, this is a pretty rare scenario. How could we ever know sigma, the standard deviation of the population, without knowing mu, the average of the population? Pretty rare. So today, we're going to look at the second of two scenarios. So our two scenarios for today are the equivalents of these, right? And again, this is me talking about hypothesis testing, what you're seeing on the screen here, but we're going to talk about the confidence intervals that are sort of associated with these types of scenarios here today. So you should expect to see some S over root n stuff. You should expect to see some square root of PQ over n stuff here today. Those terms are going to follow us around here. So example one. So let's talk through our example here first. And by the way, you can see it in this upper right hand corner here, if that's visible to you there. Can I zoom in on this more? This is just a pretty long one here. Suppose a researcher discovers a new species of beetle in the Amazon. She would like to gather basic information about the species, and so she sets out to capture a few, but she only manages to catch 13 of them, right? We're in the Amazon, hard to find certain bugs. Of the 13 that she caught, their average length was 34.2 millimeters, and their standard deviation in length was 4.1 millimeters. Because other well-studied species of beetle have normally distributed lengths, she assumes the lengths of these beetles are normally distributed as well. We would like to determine a 92% confidence interval for the true average length of this species of beetle. So let's talk through a couple things that we just saw right here. I'm going to get this a little bit out of the way right here. First, let's just identify the basic information that we just saw. I'm just going to go through each of the numbers in the paragraph and sort of extract them. First number that I saw was 13. What does that represent? That looks like the sample size. 13 total individuals were collected here for us to gather our information. So it looks like our sample size is 13. Of the 13, the average of their average length, the word there is actually really important right here. There is telling me that these pieces of information that are coming up are from the sample, not from the population as a whole. So that tells me that the sample average length was 34.2. That tells me X bar is 34.2. I'm also seeing here their standard deviation. So very importantly, this might be the most important word in this whole dang paragraph right here. This is telling me that the standard deviation information that we have does not come from the sample or from the population as a whole, but it comes just from these 13 beetles right here. So this is not sigma information. This is S information. Our standard deviation of the sample is 4.1 millimeters here. What's up with this next paragraph here? Because other well-studied species have normally distributed lengths, she assumes the length of these beetles are normally distributed as well. Here's the deal. Since we have fewer than 30 individuals in our sample, we need to know that the underlying individual distribution is normal. If our sample size was 30 or more, and again, our sample size here is 13, if our sample size was 30 or more, it wouldn't matter what the underlying distribution is. So let me kind of just make this statement here. If n is greater than or equal to 30, underlying distribution doesn't matter. If n is less than 30, need to know underlying distribution is at least approximately normal. All right, and this is a pretty, in a sense, a sort of soft thing that I'm saying here. One, that things need to be approximately normal. Two, this cutoff of 30 is a little bit more wishy-washy. It's not like a hard line right at 30. If you've got a sample size of 29, then that's probably going to be good enough right there, kind of thing. But the important thing here is we can't, the central limit theorem is what allows us to use these normal shaped distributions here. And so it's really important that if we have very small sample sizes, that we know that our sample is being drawn from an approximately normal underlying distribution here. I think it's very, very reasonable to estimate that things like lengths of literally any species of anything are going to be normally distributed. There are, I would go so far as to say, most biological indicators like length, like weight, like wingspan, stuff like that. Lots and lots and lots of those things are normally distributed for most animals. And by the way, I should say, think continuous variables for biological things are typically normally distributed. When we talk about counting things like number of eggs in a nest or something like that, those typically are not normally distributed. Those are a little bit more likely, I believe, to follow a Poisson distribution, which we haven't talked about in this class here. But so many biological measurements like that that are continuous are normal. So I think this is a very, very reasonable assumption for a researcher to make, even if this is like a brand new species of beetle. I think it's a very reasonable estimation to make. So basically all this is saying, this last sentence right here is helping us say, okay, it's going to be appropriate, even though we only had the sample size of 13, it's going to be appropriate for us to go ahead and move forward with our Z or T distribution information things here. So Z versus T hypothesis test statistic. I just kind of want to state what our general forms of these things are going to be. Then we'll actually compute the confidence interval. The reason I want to keep on bringing up the hypothesis test up is just so that we can keep on seeing that the breakdowns of our different hypotheses tests are exactly the same as our breakdowns of our confidence intervals here. And so kind of learning these side by side is going to be a valuable thing. So when we came up with our test statistics for our hypothesis test, we found the Z test statistic of x bar minus mu over sigma over root n. Notice we're not doing stuff like this here because we know S, not sigma. In our case here, we would be looking, if we were performing some form of hypothesis test, we would be using a T test statistic, x bar minus mu over S over root n. This is our scenario here because we do know S, not sigma. Our confidence interval formation then is going to follow this exact same pattern that you're seeing right here. Our confidence interval format is always going to be our point estimate plus or minus our margin of error. Our margin of error is always going to be our critical value times the standard error. All right, so this is our general formation of all confidence intervals right there. And that's exactly what we're going to see right here. If we are looking for our point estimate, so I'm going to kind of make my distinction right here so that I keep my Z stuff and my T stuff distinct right here. If I'm trying to form a confidence interval for a population average, my best estimate is going to be my sample average, x bar, plus or minus. What I want to know is how many standard deviations away might it be, and how far is one standard deviation. The number of standard deviations, I'll just say it right here, is our number of standard deviations. In this case would be what we called Z star, whereas Z star is exactly how far away in standard deviations the boundary of your middle percentage is, where the percent, as you're seeing in this problem right here, we see that 92% confidence right there. So I would look for the middle 92% of a or a Z distribution or T distribution, and wherever that upper bound range is, the upper bound location of that middle blank percent is always what we're referring to as Z star here. It's our critical value. It's our boundary between that middle desired percent and the tail. So we're going to get Z star here. That's the number of standard deviations times the length of one standard deviation according to our sampling distribution, which is our sigma over root n. On the other hand, over here, if we're using our T distribution information, the only thing that changes is we know S instead of sigma, and therefore we want to use a T distribution instead of a Z distribution. So my best guess is still going to be my sample average. I'm still going to compute my number of standard deviations away, but I'm going to use a T distribution. So we'll call this T star instead of Z star, but our concept is exactly the same. In a T distribution, which is still relatively bell-shaped, there is going to be a middle 92% of the data, and we're always going to look for the T value, that is the cutoff between the middle percent and the upper tail, and that's what we're always calling T star here. We then want to multiply by the length of one standard deviation according to our sampling distribution, and in this case the only difference is it's S over root n instead of sigma over root n. So this is what we did yesterday for our confidence interval. This is what we're updating it to today. You should notice that very little has changed right here. We're just talking about the T distribution instead of the Z distribution because we know S instead of sigma. And that's the only other swap we made. And the S sigma thing is even partnered up, right? Sigma changed to S, and because of that, Z changed to T. That will always be a partner pair, Z and sigma, T and S. Always, always, always right there. So let's go ahead and build our confidence interval. This is exactly the structure of the confidence interval that we are interested in. And I should say right here, I guess, our confidence, 0.92 or 92% right there. So that's all the information that we need here. So to build our confidence interval, maybe I'm going to go ahead and rewrite our information here. So what do we got? We got an n equals 13. We got s equals 4.1. We got x bar equals 34.2. And we've got our confidence equals 92%. We just determined that our confidence interval formation, this guy up here, we're looking to build something that looks like our point estimate plus or minus our number of standard deviations away to the boundary according to our confidence times the length of one standard deviation according to our T distribution. So let's see if we can identify what each of these pieces are going to be. First things first, x bar is easy, given to us. Our center of our guess should be what our sample average was. Our best guess from you is x bar. But we know that the sample that we collected, especially because it only had 13 individuals in it, could have had some variability relative to the true population average. So we want to give a whole window of possibilities surrounding it here. So it looks like this is going to be 34.2 plus or minus. I don't know my T star yet. We're going to have to go get that guy. I do know S, it's 4.1. I do know N, it's 13. So I actually know all my parts other than just what T star is. So when I'm thinking about computing T star, I'm picturing that there is this, and by the way, this is my low flat distribution right here because we have a very small sample size here. So this is my T distribution with 12 degrees of freedom. Remember that our degrees of freedom, there's this kind of dumb little switch we have to make between sample size and degrees of freedom. It's very simple. Degrees of freedom is our sample size minus 1. What we're interested in finding here is where is T star. T star is always going to be the upper bound of the middle confidence percent right there, right? So we are interested in finding the estimate surrounding our middle 92% right here. We are interested in where T star is. This is the cutoff between being in the middle 92% and not. So the way that we should think about this now is if 92% is in the middle, then that must mean that 8% is left over for each of the two tails. If the two tails are equally splitting that 8%, then it must be the case that there is 4% in each of the tails. And if there's 4% in each of the tails, then this tells me that 96% of the area is left of T star. And so that tells me that when I go to Excel to do my computation to find T star, I am not using 0.92 as my probability because 92% of the area is not what's left of T star. There's an additional 4% that's to the left. It's one of the two tails is also included there. So in a 92% confidence interval, we use 0.96 as the area to the left of our critical value, T star, right here. So let's pop over into Excel and see if we can compute this value here. I'm going to call this T star. Let's see, T star 92 is what I'm going to call this guy right there. It's the T star value when n is 92. What I'm going to do here is I know what my probability is. I know from my t distribution I want to get out 0.96 to the left. So maybe let's say probability that our t value is less than T star equals 0.96 says let's use t dot inv 0.96 true. We're going to do the inverse because we've been given the probability. We want to know the t value. So I'm going to come over here and do exactly that. I'm going to do t dot inv. And that's all we get for the command right there, t dot inv. It's going to ask me only for a probability and a degrees of freedom. So I just lied right there. The inverse always has the cumulative thing right here. This is going to be our degrees of freedom right here. This is therefore going to be our 12. Our degrees of freedom is what sits in that slot right there. So I'm going to go ahead and give a 0.96 and degrees of freedom is 12. Remember that the kind of weird thing here is that there is, like, as far as standard normal distribution goes, there's one z distribution that exists. For the t distribution, on the other hand, the shape is slightly different depending on how large your sample was because we have more information for the sample. S is closer to sigma as n gets bigger and bigger and bigger. So these t distributions, there's actually an infinite number of different t distributions, and we specify which one by the sample size minus 1, which is our degrees of freedom. So that's why I'm giving 12 instead of 13 here. And when I do this, it's going to tell me that this is representative of a t star value of 1.9123. I'm going to keep this as just 3 decimal places here maybe. I would say never go less than 3 decimal places on your critical values here. Keep more if you want. Never keep less than 3 decimal places on these guys. So this is telling me that according to my t distribution, the sample that, that 92% confidence is associated of being within 1.912 standard deviations of the mean of this distribution here. If you are within 1.912 standard deviations in this distribution, then you are within the middle 92%, and that's exactly the type of observations that we're interested in capturing in our confidence interval here. So it looks like we're ready to just do the computation here now. 34.2 plus or minus 1.912 times 4.1 over the square root of 13. It's typically very good form for you to list these both in the plus or minus form and in the interval form right here because they both kind of give us 2 different pieces of information. Move this. I might as well just go to the next page for this, right? Yeah. All right, so let's go to our calculators here and get some computation going on here. I've got 1.912 times 4.1 divided by the square root of 13. That's given me 2.174. So this tells me that my interval is centered at 34.2 with a margin of error of 2.174. So this says to me, I think the population average is 34.2. That's my best guess. I am 92% confident that it's within 2.174 of that. Okay. We can go and compute the upper and lower bound here. Our lower bound would be the 34.2 plus 2.174. Our upper bound Oh, sorry, that's our minus right here. Our lower bound is when we get the small number, so it's always our minus. Our upper bound is our large number, 34.2, so it's our plus 2.174. And what are we going to get here? 34.2 minus 2.174. I'm getting 32.026. And here I'm 34.2 plus 2.174. I'm getting 36.374. So let's go ahead and make some statements about these guys here. I'm going to make two different conclusion statements here. So that's one formation of our answer. Another formation for our answer here is a 92% confidence interval is from 32.026 to 36.374. So that's another good formation of a final answer right here. But it's always good for us to actually give statements that actually interpret these things. So we should do that. So I'm just going to say conclusion version 1. And version 1, I'm going to reference this information up here. Our best estimate of the population average is the sample average, 34.2. We are 92% confident that the true population average is within 2.174 millimeters of the sample average. Another way that we could state a conclusion to this based on the things that we've got is our version 2 might go with our interval 2. We are 92% confident that the true average length species of beetle is within the interval 32.026 millimeters and 36.374 millimeters. And notice that each of these are kind of good in different scenarios right here. It kind of depends on what you want to know. If you want to know what the actual span of possible values are, then this is better. If you want to get a better sense of like, and how far off might we be, then this is better. Sometimes it's nicer to actually see the margin of error term, the 2.174 right there, and to see where it's centered. Other times it's better to see where the endpoints are located on the interval right there. It really depends on the context as to which of these we sort of prefer to see in a certain setting. So I just want to say that like I kind of consider both of these to just be alternate versions of the correct final answer. And I think that in your by hand homework this week, I think I made some statements that's like be sure to state your answer in both formations, both in the, you know, point estimate plus or minus margin of error format, as well as the lower bound, upper bound format right there. Just because I think that's kind of just good practice to do right there is to understand that we can interpret both of these in a sensible way relative to our level of confidence associated with the interval that we built right there. So hopefully that you see this as very, very similar to what we did last class. Our big distinction here is that because we don't know sigma, we don't know the population standard deviation, we only know S, the sample standard deviation. That means we have to use the t distribution. All the time that you use the t distribution, you have to reference your number of degrees of freedom to compute any probabilities associated with the t distribution. So my computation in Excel was this guy right here. And remember here, this graph, man, I kind of have to draw this picture all the time. All the time, all the time. This picture really, really helps me. Now, I'm going to verbalize my way through this one real quick here to kind of maybe help you get a shortcut on this one, but I still want you to draw the picture. Don't stop drawing the picture. Is that notice that 92%, it has 8% to go to get to 100%. Half of 8% to go is 4%. we ended up using 96% as our actual value for computation inside of here. So notice that what's always the case is that whenever you're going to find any t star or z star values, either one, it's going to be the same thing, that our percent confidence, you can always close the gap by half to 100, and that will be the value of interest because half of the remaining leftover probability is to the left. That's our 4% here, whereas half of our leftover probability is not to the left. That's our upper tail over here. So 92%, if you go halfway to 100%, that's 96%. And so 96 was our actual value of interest for the computation right there. 96% of the area was to the left of our cutoff value right there because 92% was in the middle and we have a symmetric distribution right there. All right. So computing this t-star value is really one of our key steps right there. The rest of this was just doing some multiplication, addition, and subtraction right there. So there's our confidence interval when sigma is not known. And maybe let me say, just I'm thinking of the last summary things I should say here. Keep this stuff in mind. It matters that there are certain conditions that we meet for us to even be allowed to perform these types of computations. Computing this t-star would not have been appropriate if we didn't know that our distribution was going, if our underlying distribution was going to follow an approximately normal distribution, so that we could believe that when we take sampling groups of 13, that those are shaping up to be normal enough that we can use our z or t distributions there, right? So these matter right here. It matters that we either have at least 30 members in our sample, or if it's less than 30, we need to know that the underlying sample is approximately normal. So this last sentence here, although it gives you no numerical information, it gives you some sort of like requirement meeting information. This says we have met the requirements associated with using this procedure here. So that does matter. This kind of says none of our math would have necessarily been correct if this statement wasn't known right there. That was important. Okay, so that was good. We formed a confidence interval here. Let's go ahead, and we stated 2 verbal conclusions for this, by the way. You should expect to have to state some conclusions like this. So let's go ahead and take a look at our next example here. So now we've seen 2 confidence intervals. We've seen one when sigma is known for means. We've seen one when sigma is not known for means. That was the one we just did. Now let's go ahead and take a look at some proportion type stuff here. And you should notice right away on my screen right here, I have some discussion about restrictions, about the requirements that are associated to perform the hypothesis test and confidence intervals. So again, we're going to have a little bit of conversation here about when is it appropriate for us to perform these calculations and when is it not. Although this one is a little bit less extreme of as well. Okay, this restriction does not come up as often right here. Maybe I should say that. Statements about extreme are going to be misleading here in a second. You'll see why. So example 2. A pollster, a person that works for a polling company, has been tasked with estimating the level of support for a certain candidate in a city. This pollster is going to sample 73 people and find that 39 of them support the candidate. I would like to form a 94% confidence interval for the true proportion of residents in the city that support the candidate. All right. So I think a good thing for us to do here, like we did last time, is just to kind of state what we know, and then we'll talk about these restrictions, see if we meet them or not, and then we'll attempt to build our confidence interval here. So again, my usual thing is just to walk through and see if I can pick out what each of the numbers represent. He samples 73 people. That tells me right away that 73 has to be my sample size. 39 of them do support the candidate. So therefore, when he said, do you support this candidate? They said yes. That means to me, we're counting those as our successes here. So I'm going to define my successes to be X. That's a very typical variable for that. And that means to me that 39 is my number of successes that we saw. These 2 pieces of information are going to be able to allow us to compute the proportion of successes that we saw in our sample. So recognize here that we're not talking about P, that's our population proportion. We're talking about P hat or P prime, our sample population, or our sample proportion here. So this is P hat is always going to be our X over N. It's just our proportion. What percent of people said yes? It's 39 out of 73 people said yes. And so real quick, visit the calculator here. 39, turn it on, 39 divided by 73. And that's showing me 0.5342. All right, so I know what my sample proportion is. Remember, we're trying to estimate a population proportion, and our best guess for the population proportion is always going to be our sample proportion. Just like in our previous two examples, our best guess for our sample or our population average is our sample average. Right? So that's an important piece of information for us there. The other thing that we know is that we have a confidence level of 94%. Um, And so before I kind of walk away from this stuff right here, I guess the other thing that I want to do, I'm going to scroll back up and revisit our original statements here about how our information is distributed here. What we're saying here is that it looks like we are wanting to center our information at our population proportion, but again, we don't know that. The piece of information that we really need here is the square root of PQ over N, right? So it looks like I've been given this standard error term. I can see it in my test statistic. I can see it in my distribution right here. Our standard error is PQ over N. You ready, computer? Can we go back to doing this, or are you going to pause on me again? Okay, come on, computer. You got to catch up with me here. Come on, come on, come on. You can do it. Now, the important thing to see here is this. This is suggesting that we're going to use P times Q divided by N, but we don't know P. Is my computer just freaking out right now? I am getting everything being all draggy right now. What is going on here? Calm down, computer. Calm down, computer. Should be doing nothing else. We're just writing right now. Okay, so it should be PQ over N. I'm going to write this one more time because apparently I'm not allowed to write today. Okay, let's try this again. Maybe we're back to being allowed to draw again. There we go, that's nice. So what we're going to do is we're going to estimate them. With our sample statistic information there, our P hat, Q hat over N. So this is going to be good because this is going to get us one of our key pieces of information that we need to know for our confidence interval here. So our restrictions on the hypothesis test and the confidence intervals for proportions. So there is one restriction that's associated with this, and I'll describe to you. I think this one hopefully makes a good bit of sense right here. Our restriction that we're going to have on our hypothesis test and confidence intervals for proportions is that both NP, put this in math formatting, and NQ are greater than 5. Now, what are NP and NQ? N is our sample size, P is our probability of success, Q is our probability of failure. Remember that NP is our sample size times the probability of success. So NP is our expected number of successes, and NP is our expected number of failures. All right. So basically the deal here is that we need to take a sample that is big enough that we expect to get at least 5 yeses and at least 5 nos. All right. So basically, the bottom line is this. We need to take a sample large enough that we expect to see at least five successes and at least five failures so that our distribution will be approximately normal, so that we can use our z distribution to actually compute probabilities of interest, get things like a z star value. So let's think about when this won't happen. Or at least maybe let's think about when this should happen here. You should notice here that n times p, I mean, notice here that we're getting like 50% for our sample proportion. So even though we don't truly know p in this case right here, it does seem like we have some pretty middle of the road support for this candidate, about 50% support for this candidate. So it looks like we are expecting to see like 30 something successes and 30 something failures, right? So it looks like we've totally met the conditions in this case right here. The thing that we want to be weary about doing is things like this. What we don't want to go trying to do with this confidence interval for proportions is to do things like say, I'd like to estimate the proportion of the population that has brain cancer. I'm going to go sample 200 people and ask them if they have brain cancer. What's probably going to happen is you're going to go sample 200 people and probably find maybe 0 or 1 people that have brain cancer out of 200, right? Because it's a really rare thing. It's a very, very small probability. So if I sample 200 people, I'm not expecting to see five yeses at least, let alone five no's. Obviously, I expect to see that, but I really don't expect to see at least five people tell me, yeah, I have brain cancer. And so in that case right there, if we're expecting that maybe like for example maybe 1 in 300 people have brain cancer, that would say to me we have to take a sample at least of 1,500 people, because if 1 in 300 have it, then out of 1,500 people we'd expect five people to have it. That would then meet our threshold right there. So this is saying if you're going to try and discuss proportions of events that are very rare or extremely common, right? Successes or failures being extremely common. If we're talking about something where there's a 99% chance of success or a 99% chance of failure, then you have to take a very, very large sample to meaningfully phrase up some confidence intervals. And that's because changing by just one observation could make a huge difference then, right? If I sample 200 people, there's going to end up being a massive difference between me seeing 0, 1, or 2 people that have brain cancer out of 200 people, because 2 people is twice as many as 1 people. That's a twice as extreme sample only because of one yes observation right there. So basically things get a little wonky and skewed if you're at the extremes here. So basically your only word of caution associated with hypothesis tests and confidence intervals for proportions is you need to expect to see at least five successes and five failures, or else your distribution is going to be so skewed that we can't appropriately use our normal distribution to compute the surrounding probabilities. So this is really just a restriction that just says, watch out for extreme probabilities. If you ever see a 1% or a 99%, you should immediately say, oh man, we better be taking a huge sample or this isn't going to be legit. All right. The more extreme to the edges our probabilities are, the larger the sample size needs to be for us to see normally distributed outcomes for our samples here. All right. So this is basically our only major restriction for our proportion statements, confidence intervals, hypothesis test is expected number of both successes and failures has to be at least five. And we've certainly got that here. Our expected number of yes votes here is about 50%, and therefore our expected number of no votes here is about 50%. So we certainly see at least five expected yeses and nos out of a sample of 73 people right here. On the other hand, though, notice, and I'll stop talking about this in 1 second, notice that if we took a sample of only like 7 people here, then we wouldn't necessarily expect to see five successes and five failures. Notice that in this case, this is in a sense saying to us, you basically have to have a sample of at least 10 people, or else you couldn't even have five successes and five failures right there, right? So this in a sense also does put like a lower bound limit on what we could expect right there. So maybe this is worth saying right here. Um, Right. So this statement is not really about sample size. This statement is about expected number of successes and failures, but we're sort of gleaning this secondary information about sample size out of here as well. It's just kind of a default thing with tiny, tiny samples. We haven't quite let the central limit theorem take hold there yet. But again, in this case, we have met our requirements, so we are good to go on to compute a confidence interval. So let's see the formation of our confidence intervals that we've seen. We have seen for mu, we've seen x bar plus or minus z star sigma over root n. We've seen x bar plus or minus t star s over root n. Since our proportions are normally distributed, we fortunately get to use the z distribution, which is good. Now, our questions are, what should our point estimate be for p? Notice that when we wanted to estimate the population average, we used the sample average as our point estimate. Therefore, to estimate the population proportion, we want to use the sample proportion as our point estimate. So we're going to get a p hat plus or minus. In this case, our sampling distribution of the binomial distribution of groups of apparently at least 10 right there is going to be known to be normal, standard normal. So we do get z star stuff that's associated with this. Fortunately for us, the z star value is going to be computed the exact same way as this z star value here. The only term we need over here is we need a standard error term. This is representing the length of one standard deviation within our normal distribution. Coming back up to the top, remember that we already kind of saw this, right? We saw that our standard error term is this guy sitting right here. It is what we divided by in our test statistic. And so down here, it looks like our standard error term in our normal distribution is this square root of PQ over N. The only difference is we don't know our population proportion, so we're going to have to use our sample proportion in space of that right there. So what I'm going to get here is we're going to get our square root of P hat Q hat over N right there. There is our standard error term. It's our number of standard deviations times the length of one standard deviation, and that's our distance, that's our margin of error that we're traveling from our point estimate right there. So again, we're noticing that we actually know most all this information right here. So let's kind of maybe restate what we know and go ahead and compute this guy here. We have that N is 13. We computed that P hat was, what did we get P hat to be? 0.5342. Remember that Q hat is always going to be 1 minus P hat. So I can go to my calculator real quick and do that guy. 1 minus that guy is going to be 0.4658. Our success, our probability of failure is just the complement of our probability of success. Okay. What other terms do we need here? I'm looking at my statement right here. It looks like we've kind of got everything we need. We need N, P hat, Q hat. We got those. We need P hat. We're going to need Z star again, like we'd said. So let's go ahead and form up our confidence interval here then. Should be our point estimate, P hat, plus or minus our Z star value, our critical value associated with our percent confidence. We're doing 94% confidence, by the way. Times square root of P hat, Q hat over N. So let's fill in the values that we know. 0.5342 plus or minus Z star, we still don't know. We're going to go find that in 1 second. Times, this will be a bit of a grosser one right here. P hat is 0.5342. Q hat, 0.4658. And remember, it's just 1 minus P hat right there. You could just throw that in that way in your calculator. Divided by N down here is going to be our 13. And so it looks like our missing piece that we still need is Z hat. And we've got everything we need to make this computation happen here. So, or sorry, Z star. I think I just said Z hat. So to get our Z star value, I think, okay, I'll do it right here. We are looking at our standard normal distribution. We are interested in our middle 94%. If 94% is in the middle, then that means that 6% is in the tails, evenly distributed. So that should mean to me that there's 3% in this tail, and there's 3% in this tail. Our Z star value is always our upper bound cutoff right there. It's always saying How far do we go left and right to get to that 94% boundary right there? So how much area is to the left of z star? Probability that we'll get a value less than z star, it looks like, is 94% plus an additional 3% for 97%. And notice, just like we said before, we're closing half the gap to 100% from 94%. 94% has a 6% gap to 100%. Half of that is 3. And so that's what we've tacked on additionally. Close the gap by half right there. So we can come over here into Excel and actually get this value now. So this should be my z star for 94%. And in this case, I'm going to use my z, my norm.inv. And this one I have to tell it that it's standard normal. Z means the mean is 0 and the standard deviation is 1. Our probability here is 0.97. Our mean is 0 because it's a z distribution. Our standard deviation is 1 because it's a z distribution. And this is going to give me 1.881. We'll round that to 3 decimal places there. And so what are we getting here? 0.5342 plus or minus 1.881. That's the number of standard deviations away we need to go to get to the boundary of 94% times, and let's stop marking that mark right there. I'm going to go to my calculator and throw this guy in here now. We've got a 0.5342 times 0.4658 divided by 13. And I'm going to take the square root of that guy. And I'm getting 0.1384. So I can multiply my 0.1384 times 1.881. And I'm going to get 0.2602. That seems awfully wide to me there. Is that really our... Yeah, I suppose that is our... that seems very wide to me right there. An extra 26% of leeway in each direction right there. Yeah, I mean, I guess we want to take a bit bigger of a sample there then, huh? This is a pretty small sample that we're taking if we're trying to judge the, um, an entire city's... Oh, wait. I see what I'm doing. Okay, okay. All right. Notice that I got myself confused with my previous problem up there. I'm still using my sample size of 13, which is not correct right here. Our sample, I was like, dang. So hold on, let me point out to you, by the way, this is a great thing to do right here. I'm glad I made this mistake. You should immediately be like, dang, really? That's a really huge confidence interval. This says to me we think that 53% of people support the candidate, give or take 26%. That's ridiculous right there, right? That basically says to me it's anywhere between about 25% and 75% support for this candidate. That's a huge, that's basically giving us no information. That's like the support for literally every candidate, right? Notice here, I'm taking my information wrong here. I kind of recognized, importantly, I felt like that was crazy. And so that led me to kind of stop and say, wait, is that right? And I immediately found a mistake that I'm catching for myself right here. So notice in our description right here, 73 is our sample size, not 13. 13 was from the last problem right here. It was 73 is our sample size here. Did I make that mistake when I wrote it out up here? No, and it's 73. Okay. So all I got to do is just change this 13 right here to a 17 or 73. There we go. And now I'm going to go redo this calculation right here. So now I'm going to get 0.5342 times 0.4658 divided by 73. Take the square root of that guy. And now I'm getting a much more reasonable answer right here of 0.0584. So this is telling me that my, oh wait, I have to multiply by the 0.1888 or 1.881. So we still are going to get a kind of wide interval right here, but not super and not as crazy wide as it was a second ago here. So now I'm going to multiply this guy by the times 1.881. So it's going to be almost twice as wide here, but I'm getting 0.1098. So the point here is this apparently wasn't a very big sample for us to take to get very good information right here. We're not sure about the support for this candidate, give or take almost 11% out there. All right, so it looks like we're going to be getting here for our upper bound and for our lower bound. I'm going to do my addition and my subtraction here. Let's see here, 0.5342 minus 0.1098 is 0.4244. All the way up to 0.5342 plus 0.1098 is 0.6440. We might interpret this as 42.44% to 64.40%. Now, let's talk about two reasons why this is such a wide interval right here. So that's a pretty good response. That's a pretty good response right there. That's a pretty good response right there. These are all ways that we might phrase sort of our final answer right there. All right. So let's formalize our statement right here. We estimate the population proportion of support for the candidate to be 53.42%. We are 94% confident that the estimate is accurate to within 10.98 percentage points, and I'll say percentage points, just to be clear about my percent right there. Alternatively, a different statement that we could make is we are 94% confident that the true proportion of residents that support the candidate are between 42.44% and 64.40%. Right? So this is a very wide interval. Two reasons why. 94% is a relatively high confidence level, which leads to a relatively large z-star. Right? So one thing that's true here is that since we wanted to be 94% confident that we were capturing the true value, our interval had to get wide enough to be 94% sure. If we were only like 80% sure, if we only need to be 80% sure, we can make a smaller interval because we'd be okay with being wrong 20% of the time. Right? So that's one reason why that's a little bit wide. The sample size of 73 is not huge. A larger sample size would reduce the margin of error. And so the thing that we know about all of our margin of error terms, right? We've listed all of our forms of confidence interval are sitting right here. And notice all three margin of error terms divide by n. So as n gets bigger, margin of error gets smaller. That's a general statement for all confidence intervals. The more information you know, the narrower of a range we can pin down where the true purport or population parameter is going to live. So the more n we have, the better we can do. So that should immediately lead you to what we're going to get for our final question right here, which is, well, how big does the sample size need to be to get more desirable margin of errors, right? So the point is, small margins of error are much better because they give us a much more specific picture of where the true value is. This is basically useless information for any candidate right there because pretty much all major candidates get about that much support, right? Like every presidential election in history, I think has had maybe like one or two have been so extreme that their amount of support for one candidate or the other has been more extreme than either of these two. Like this isn't quite good enough information, right? So it seems like we want to sample more people. So let's say this now instead. A pollster has been now tasked with forming a confidence interval about the level of support for a particular candidate. Her boss would like the poll to have a confidence level of 95% and a margin of error of 2%. How many people must be polled to guarantee results with these features? So you should notice what's super important here is we don't even have sample information. Where'd my size go here? So let's talk through this one. This one's going to have a little bit of a weird estimate that we're going to make, but hopefully you're going to completely kind of agree with it and that it's understandable as to why we would make the estimate that we're going to make right here. So here's kind of where we're at. We have really only been given the fact that we would like to have a confidence level of 95% and a margin of error of 2%. So our confidence level is 95%. And so we can go ahead and figure out what our Z star is. That goes with 95%, right? This should be, what's our probability that we want to use here? If we've got our middle 95%, then that means that 5% is shared between the two tails. If 5% is in each of the two tails, then that's 2.5 and that's 2.5. And therefore, where our Z star is located is going to have to be located where 97.5% of the area is to the left. So we are interested in the probability that the Z value that we see is less than Z star being 0.975. Right? So let's go over to our calculator here and do exactly this, 0.975. So we're going to do our norm.inv, our inverse normal computation. What's the probability? 0.975, 97.5% is to the left. Mean 0, standard deviation 1 because we're standard normal. And that's going to tell us 1.960 it looks like. And by the way, this is pretty standard. I feel like, I don't know, at least in teaching stats, I've got the 90, 95, and 99% confidence intervals are by far the most common. I don't know. If you were to say to me, hey, Tony, what's the number 1.960 represent? I'd say to you, oh, it's the Z-star value for 95% confidence level because I've seen that value a bunch right there. I think that you'll end up kind of recognizing a bunch of these here as well. So what do we even know here? We know the margin of error we want to be 2%. So what represents the margin of error? Our confidence interval is going to be p hat plus or minus z star square root p hat q hat over n. And remember that this is the margin of error. So here's what we're going to do. Oh, you jerk. I'm pressing end. I swear okay. All right, so here's where we're at. We're not interested in the entire confidence interval. We're not trying to form one. This person's just saying, my boss told me I need to produce some stuff with this features right here. The question is, how many people must be polled? We're trying to find n. All right, we want to know what's the sample size required to get this kind of stuff. So we're trying to solve for n in this case here. Notice that at no point is the entire confidence interval referenced. We weren't given a confidence interval. We're not asked to produce a confidence interval. The only discussion is about the margin of error, which is the second part of our confidence interval terms right there. And we know what we want our margin of error to be, and we know one of the terms in our margin of error right there. So let's put all three of these pieces of information together here. Um, so to say our margin of error is going to be 2% says to me z star square root p hat q hat over n is equal to 0.02. That says my margin of error is equal to 2%. I've grabbed the margin of error terms. So what am I going to do? I'm trying to solve this guy for n. And here's kind of my pickle. Well, I don't know p hat or q hat. All right, so here's what we're going to do. Let's see, should I do my solving steps here first? I think we should. So let's go ahead and solve this guy for n. Let's do the algebra to solve for n. Then we'll come back and figure out what the heck are we going to do about the fact that we don't know p or q right here. So I know z star. Z star is our 1.96. So I can divide by the 1.96. I want to undo a square root, so I'm going to go ahead and square both sides. My new issue is that I really want my fraction flipped there, right? I want n in the numerator so I can solve for it much more easily. So fortunately, if one fraction is equal to another fraction, then the reverse of those two fractions should also be equal, the reciprocal of those fractions here. So I can make the flipped statement here that says n over p hat q hat equals 1.96 over 0.02 squared, right? I've flipped the fractions on both sides here. And now as my final step, I'm just going to multiply by p hat q hat over to the other side over here. So my whole issue here is this. I don't know p hat, and if I did know p hat, I'd know q hat. Right. So here's my deal. I really need to make sure, I need to make sure that no matter what the sample proportion is that we get, I'm still going to have the satisfactory number of observations. So p hat, q hat might be small or it might be big, right? There's different sizes that this could be. Um, So let's just walk through some examples here. If we found that our sample proportion was 20% support, then that would mean that there's 80% not support, in which case p hat times q hat would be zero point 0.2 times 0.8, which would be 0.16. And again, I'm just saying some estimated values right here. What if we got 30% support for the candidate? That would mean 70% non-support for the candidate, and that would mean that p hat q hat would be 0.3 times 0.7, which is 0.21. Notice that it's a little bit bigger right here, suggesting, therefore, if our support was 30% instead of 20%, we would need a larger sample size to keep our margin of error small, right? We're interested in this quantity. This is our p hat q hat. And notice as p hat q hat gets bigger, the required sample size gets bigger. Let's say that here. So again, we're using this statement in the box as our guiding statement. As the value of this multiplication gets bigger and bigger and bigger, the value of n, the required sample size is also going to get bigger and bigger and bigger. So maybe our question might be, what's the biggest that p hat q hat could be? And by the way, remember that it's phrased like this. Also, an alternative phrasing is the p hat times 1 minus p hat. What's the biggest it can be? So I'm gonna kind of tell you the answer right here, but I'm gonna show you exactly why I know the answer. If you picture this guy right here, for you algebra people, right? So this is for all of you that remember your quadratic equations right now. Oh, that's not where I think you thought I was going with this guy right here. If we picture this as like the quadratic equation, y equals x times 1 minus x, then I know that this is a parabola that has a root at 1 and a root at 0. And because we're going to get a negative x squared term, it's going to be a parabola that opens down. Right now, I know that not all of us have taken algebra. Even those of us that have, I'm positive that many of you have forgotten these little graphical tools available for us here. But notice if this is at 0 and if this is at 1, our question is, what is the maximum value of this? What's the biggest it ever gets to? And what we can see right here is that we're going to get to our largest value when we're exactly halfway in between 0 and 1, which is at 0.5. And so what that's going to say to me is that if p hat is 0.5, that's our 50% success, then in that case, we're going to get 50% failure. And that's going to tell me that p hat q hat equals 0.25. 50% times 50%, half of half is a quarter right there. So this is the largest that this could ever be. So what I'm going to kind of say here is, this is going to do it to me. I know you're going to do it to me. Oh my gosh, it didn't do it to me. So let me just come down here and actually type it out. So come on, font. I'm trying to wrap it up here. We're almost done. We got this guy here. If I can just get this thing to quit being ridiculous to me. Okay. I'm not trying to save right. What are you doing? So here's the deal. All right, let me kind of come back up and then I'm going to rewrite this or reread that paragraph right there. What we found is this. If I want to know the required sample size n to achieve a desired margin of error, which we have given as 2%, 0.02 here, my answer is going to depend on what our actual sample results are. But we haven't taken the sample yet. The whole point here is we need to know how many people to sample. So this is sort of a chronology issue right here. I need to know my margin of error first, but to know the margin of error, I need to know the sample proportion first. But I need to know the sample proportion, I need to know how many things to sample. So this is a chicken or the egg issue right here, right? Which one's going to come first? But what I can picture is this. I know that p hat times q hat can take on some span of values. And with a little bit of algebraic help right here, I can see that the possible values it can take on, if we were to like go and graph this thing more carefully, we'd see that all possible outputs from p hat times q hat, since it's always going to be a number between 0 and 1 times its complement, is always going to be at its most extreme. The largest p hat times q hat could ever be, no matter what sample you draw, is 0.25. The most extreme scenario is a 50-50 split. And if it's 50% yes, 50% no, then the product of those is 25, 0.25, 25% right there. So the largest, no matter what type of sample we draw, this is guaranteed in a sense, cover us right here. This might therefore end up giving us a larger sample size than we actually needed if we see not close to 50-50, right? If we take a sample and find 20%, 80% for the yeses and nos, then it's going to be the case that we're going to have collected a larger sample size than we would have needed because we're going to estimate sort of the worst case scenario p hat q hat. And when I say worst, I don't mean there's like a bad outcome. I just mean the most numerically extreme. The most numerically extreme outcome from p hat q hat is 0.25. It's the largest it could ever be. That's going to give us the largest n we might need. This is saying if you had a 50-50 sample, that's going to require the most sample size to get that margin of error of 2% that you want. So let's prepare for this worst case scenario. Even if it's a 50-50 sample requiring the largest margin of error, or requiring the largest sample size, we'll still have a sample size that's big enough to get us the desired margin of error. So what we always do here is we always estimate p hat q hat to be, in these scenarios, we let p hat q hat equal 0.25. The largest value p hat q hat could take on. Which gives the most extreme n we might need. So we'll for sure get our desired margin of error. Regardless. Ugh. Try that one again. Regardless of the observed sample proportion. So all we're going to do is come back up here, grab our semi-final statement, right? We got down to this guy right here. I'm just going to grab this, 1.96 over 0.02. And that's going to tell me how many do I need to get that guaranteed 2% with a 95% confidence interval. 1.96 divided by 0.02 squared times 0.25. And that's going to tell me, holy cow, I need a lot. That 2% margin of error is pretty dang small right here. I'm getting here 2401 exactly. This says to me I need to sample 2,401 people if I want to be 95% confident with a 2% margin of error right here. Say one thing. So notice here that if I had gotten that I need to sample 24, say for example that n was instead 2,400.1, then that would say that I would need to sample that additional 0.1 of a person to get over my threshold. But there's not 0.1 of a person, right? So anytime you ever get a decimal from this calculation for n, you always have to round up to the next nearest whole person. That 0.1 would not round down because 2,400 is not enough. You'd need to get up over that 2,400.1 which the next highest value would be 2,401 to get there. In this case, mine came out clean exactly like that. But if you were to get a decimal in these cases, you always would round up to the next nearest person, not using our typical round up or down at the 0.5 right there. So notice that in general, our sample size needed for specified margin of error is always going to be n equals, it looks like this was our z star, that's according to our confidence level, divided by our margin of error that was told to us, squared, times 0.25. And remember where the 0.25 is coming from, is that is our worst case scenario for the value of p hat times q hat. We don't know p hat, q hat, but the biggest it could ever be is 0.25. And so we want to make sure we take the biggest sample that's guaranteed to be big enough, regardless of the sample proportions that we end up drawing from the population there. So these are really good problems. This is the type of computation that's done all the time, especially right now during election season. This is a calculation that every person that works for a polling company can do very quickly and easily. They're just thrown into this formula right here. It matters that we take polls that have a known margin of error, and you should be seeing this. Gosh, in the last couple of weeks, I have done my very best to receive exactly zero election news because it drives me insane. But every single poll that you ever read in a newspaper always lists its known margin of error. And what's always happened is they always go into these polling situations preemptively saying, we want to sample enough people that we can claim a margin of error this small. So figure out how many people you need to sample and go sample them and compute your confidence interval. And then we'll know what that might be. And again, it might be the case that you go sample these people and you find that your p hat is 0.4 instead of our worst case scenario 0.5. In that case, all that means is that your required sample size n is actually a bit more than what you need for that actual margin of error out there. And that's okay. You're still within it. If your boss tells you, I need a 2% margin of error, and you come back with a 2.5% margin of error, you just blew it. On the other hand, if your boss says, I need a 2% margin of error, and you come back with a 1.5% margin of error, then you just did good. You just did better than what was expected of you. So this is one of those things where we have to get within the requirement, and if we get a little bit more than that, that's okay. And that's kind of what's happening with our estimate of p hat q hat being 0.25 right there. So that's going to wrap it up for me for this week. We've now seen our confidence intervals for an average if we know sigma using z, our confidence intervals for an average if we don't know sigma using t, our confidence intervals for a population proportion, which is always going to use z. There's never t stuff associated with our proportion stuff. And we've seen that we can do some pretty interesting working backwards problems here in a sense of saying, what are the parameters I would need to get these results associated with my confidence interval on the other end? This is how people do planning for their sampling that they're going to need to do out there, rather than just going out and taking an arbitrary sized poll, planning to say, I know I need to sample exactly this many people to get the type of statistical results that I am wanting to get to publish in the newspaper or whatever out there. Okay. So, as always, hit me up with questions. I have given you guys a written homework for the week. If you ever want me to like double check that in any way, or I mean, literally, I'll just like look at it and tell you if you're right or wrong and stuff like that. I'll answer any questions that you guys got. Come hit me up in office hours, send me an email, all that good stuff. Otherwise, I will see you guys next week. Next week, what we're going to look at is basically all the same stuff, except we're going to look at comparing two populations instead of always just drawing from one. But we're going to look at both hypothesis tests and confidence intervals for averages and proportions. The only difference next week is comparing two groups rather than always just looking at one group. What's the difference between two groups is what we're going to be asking next week. But you're going to see so much similar math. Our structures of everything is going to be exactly the same. So that wraps it up for me today for week 10, and I will see you guys in week 11 for hypothesis tests and confidence intervals for two samples.